In the previous lecture, we have seen the discrete Fourier transform. Now we will see the next type, that is decimation in time and decimation in frequency. The decimation in time and the decimation in frequency algorithm are the typical forms of fast Fourier transform. There are two types of FFT, that is fast Fourier transform. One is decimation in time and the second one is decimation in frequency. Many hardware and software implementations are based on these algorithms. One class of the fast algorithm for computing discrete Fourier transform is based on recursive factorization of the polynomial 1 by z. The DIT, that is decimation in time algorithm, is used to calculate the DFT, that is discrete Fourier transform of n point sequence. The idea is to break the n-point sequence into two sequences, the DFTs of which can be obtained to give the DFT of the original n-point sequence. Initially, the n-point sequence is divided into n by 2 point sequence, that is xe of n and xo of n, which have even and odd number of xn respectively. That means first there is a n point sequence, then we have to divide this sequence into 2 points, that is n by 2 point sequence. One is the even and second one is the odd number of sequence. The n by 2 point DFTs of these two sequences are evaluated and combined to give the n point DFT. Similarly, the n by 2 point DFTs can be expressed as the combination of n by 4 point DFTs. This process is continued until we are left with 2 point DFTs. This algorithm is called decimation in time because the sequence x of n is often split into smaller sequences. Radix to DIT FFT algorithm. Radix to the sequence length n is satisfied by n equal to 2 raised to L, where L is an integer. To decompose n point time domain signal into n signal, each containing a single point. Each decomposing stage uses an interlaced decomposition separating the even and odd indexed samples. To calculate n frequency spectra corresponding to these n time domain signals. So here is one example of radix to DIT FFT algorithm. One signal of 16 points. So in first line there are 16 points and this 16 point is nothing but one signal. Then two signal of 8 points. These 16 points are divided into two parts. So one signal becomes two signals. That is, one signal is divided into two signals. In first part there are even numbers 0, 2, 4, 6, 8, 10, 12, 14, and in second part there is a odd numbers 1, 3, 5, 7, 9, 11, 13 and 15. Then the next line is four signals of 4 points. So here the first part is divided into 4 points, 4 points, and it consists of 4 signals. Again it is divided into 4 points, that is 0, 4, 8 and 12, 2, 6, 10 and 14, and odd part is also again divided 1, 5, 9, 13 and 3, 7, 11, 15. The next line is 8 signals of 2 points. It is again divided as 0, 8, 4, 12, 2, 10, 6, 14. Odd part again divided 1, 9, 5, 13, 3, 11, 7, 15. Then the last line is 16 signals of 1 point. That is 0, 8, 4, 12, 2, 10, 6, 14. This is even part. And the odd part is 1, 9, 5, 13, 3, 11, 7, 15. So here the signals are divided. That is, the start of this is one signal having 16 points and it ends with 16 signals of 1 point, means there are 16 signals and the 16th signal consists of only 1 point. The radix to decimation in time algorithm rearranges the discrete Fourier transform equation into two parts. A sum over the even numbered discrete time indicates n of 0 to 4 n minus 2, and the sum over the odd number indicates n of 1 3 n n minus 1, which is already seen in the previous slide. So here also in this slide given that to divide n point sequence xn into 2 points, that is n by 2 point sequence x1 of r and x2 of r. So there are two equations for x1 of r and x2 of r where the value of r ranges from 0, 1 to ... And to compute the DFTs of this x1 of r and x2 of r, the equations are given here. So the mathematical simplification of this equation reveals that all the DFT frequency output can be computed as the sum of the output of two length n by 2 DFTs of the even indexed and the odd indexed discrete time samples respectively, where the odd indexed short DFT is multiplied by a twiddle factor. So this is called the decimation in time because the time samples are rearranged in alternating groups, and radix to algorithm because there are two groups. So this figure graphically illustrates the form of DFT computation, where for the convenience of the frequency output of the length n by 2 DFTs of the even index time samples are denoted by x1 of 0, and those of the odd indexed are denoted by x2 of 0. Because of the periodicity with n by 2 frequency samples of these length n by 2 DFTs, the x1 of 0 and x1 and x2 can be used to compute two of the length and DFT frequencies, but with different twiddle factor. The direct computation of n DFT frequencies according to the DFT equation will require n square complex multiplies and n square minus n complex additions. By reusing the result of the two short length DFTs given in the figure, the computational cost is now. For that we will use two equations. At the end of the computation flow graph, at any stage output variable can be stored in the same registers previously occupied by the corresponding input variables. This type of memory location sharing is called in-place computation, which results in significant saving in overall memory requirements. So there are some equations for decimation in time radix 2. Let's explore an approach that subdivides time interval into successively smaller intervals. Assume n the size of the DFT is an even integer so that n by 2 is also an integer. So define two auxiliary signals, that is an is x of 2n and bn is x of 2n plus 1, where n ranges from 0, 1 to n by 2 minus 1. Let ak and bk denote the two n by 2 point DFTs of an and bn. For the equation for a of k and b of k can be given by this equation, can written by this equation. We can show that these are related to the DFTs by the following equations. So there are two equations. The computation of ak and bk each require n by 2 square equal to n square by 4 multiplications. The scaling requires n by 2 additional multiplication. The total computation is n square by 2 plus n by 2 multiplication, which represent n square by 2 minus n by 2 fewer multiplications than the n square multiplications required by the DFTs. For n is equal to 128, this is the saving of 8128 multiplications. Again, this diagram shows the decimation in time of length n DFTs into two lengths, that is n by 2 DFTs followed by the combining stages. So, another method of splitting the input sequence into half is as follows, that is x0, x1, x2, x3 and x4, x5, x6, x7. That is decimation in frequency is another method. So it can also be obtained that the output x of k will appear in bit reversed order, and this method is called as decimation in frequency algorithm. So it is a popular form of FFT, that is fast Fourier transform algorithm. Here the output sequence x of k is divided into smaller and smaller subsequences. That is why the name decimation in frequency. Initially, the input sequence x of n is divided into two sequences x1 of n and x2 of n, consisting of the first n by 2 samples of xn and the last n by 2 samples of x of n respectively. So radix 2 FFT algorithm principle is to divide n point sequence into two n by 2 point sequences. So the former n by 2, that is starting by 2 point xn, where value of n ranges from 0 to n by 2 minus 1, and the latter n by 2 sequence is x of n plus n by 2. The comparison of the radix to decimation in frequency algorithm rearranges the discrete Fourier transform equation into two parts: computation of the even numbered discrete frequency indices x of k for value of k ranges from 0 to 4 n minus 2, and computation of odd number indices k where k ranges from 1, 3, 5 n minus 1. The mathematical simplification reveals that both even index and odd index frequency output x of k can each be computed by a length n by 2 DFTs. The input to these DFTs are the sum or the differences of the first and second half of the input signal respectively, where the input to the short DFT producing the odd index frequencies is multiplied by a factor, that is Twiddle factor, and this is called decimation in frequency because the frequency samples are computed separately in alternating group. The radix 2 algorithm because there are two groups. So this conversion of full DFT into a series of short DFTs with simple processing steps gives the decimation in frequency. Next is comparison of DIT and DIF. The order of samples DIT FFT. In DIT FFT, the input is bit reversed order and the output is natural order, while in DIF FFT input is natural order and the output is bit reversed order. That is, input is bit reversed and the output is natural in DIT, and for DIF output is bit reverse while the input is natural order in DIF. The DIF butterfly is slightly different from the DIT butterfly, the difference being that The complex multiplication takes place after the add subtract operation in DIF. That is, in DIT FFT multiplication is done before the addition, and in DIF FFT multiplication is done after addition. Now there is a similarity also between DIF and DIT. Both algorithms require same number of operations to compute the DFT. Both algorithms can be done in a place and both need to perform bit reversal at some place during the computation. Now, why the computations in FFT algorithm is said to be in a place? Once the butterfly operation is performed on a pair of complex numbers small ab to produce capital AB, there is a need to save the input pair. We can store the results AB in the same locations. Since the same storage locations are used throughout the computation, we can say that the computations are done in a place. So this is the difference between and similarities between DIT and DIF. What is radix to FFT? The FFT algorithm is most efficient in calculating n-point DFT if the number of output points capital N can be expressed as a power of 2, that is n equal to 2m, where m is the integer, then it is called as radix to FFT. Both DIT FFT, that is decimation in time fast Fourier transform, and DIF FFT, that is decimation in frequency fast Fourier transform, have the identical computation complexity. That is, for n is equal to 2 raised to L, there are total L stages and each has n by 2 butterfly computations. Each butterfly computation has 1 multiplication and 2 addition. So both DIT and DIF FFT have the characteristics of in-place computation. A DIT FFT flow graph can be transposed to DIF FFT flow graph and vice versa. What is decimation? It is nothing but reducing the sampling rate of the discrete time signal, and the low sampling rate reduces the storage and computation requirements. Thank you.